So there is one question on it. Find the nature, find the position and the nature of the image formed. Find the position and the nature of image formed. So this is some spherical surface. This is a spherical surface. Okay. And around the spherical surface, and this surface, I means this medium have the refractive index of 1.5. This is made up of glass, and here is air, and one object is placed here at a distance of 30 centimeter, and this is the pole, and this line is the principal axis. This line is the principal axis. We know that, and this is the center of the curvature. So this distance will be the radius of the curvature. They are asking find the position and the nature of the image formed. So here refraction will take place. Refraction of light will take place because light will go from this object, from air to the glass medium. Means you can say the refraction will take place. And we want to find where the image will form. We want to find where the image will form. So how can we find where the image will form? Very easy. We have the formula for the refraction from the spherical surfaces, n2 by v minus n1 by u is equal to n2 minus n1 by r. We have the formula n2 by v minus n1 by u is equal to n2 minus n1 by r. Okay. So we will use this formula, and object distance is given. This is the object. This is the object and this is the pole. So all the distances we are measuring from the pole. So object distance will be 30, and object distance will be 30. And remember, from this object the light will go in this direction. So means this direction will be taken as the positive, because incident ray from the object will go in this direction to enter in this medium. So this direction you will consider positive, and this direction will be taken as negative. Now object distance is this, from P to O. Now all the distances I told you to measure from the pole. Matthew, is my video breaking or is my voice breaking?
Not really, sir. No.
So when you will measure the object distance, so you will measure from the pole. From the pole you will measure means you will measure the distance in this direction, and this direction is the negative direction. So this object distance u is negative. This is the object distance. Object distance is represented by small u. Now the distance between the pole and the center of curvature is known as the radius of curvature. Now to measure the radius of curvature, you will move from pole to center of curvature like this. Means from pole to center of curvature means you are going in this direction, and this direction is positive direction. So radius of curvature you will take plus 10 centimeter. And the image distance you want to find. Now we will see what is n1 and what is n2. So I told you that N1 is the refractive index of the medium from which the light is coming. So light is coming from this medium, from air medium. So N1 will be 1, and N2 is the refractive index of the medium in which the light is going. So light is going in the glass, and glass have the refractive index of 1.5. Now apply this formula, N2 by V and N1 by U, and you will get the value of the image distance. So N2 is 1.5. What is V? We have to find the V. Minus N1 is 1. Minus N1 is 1. U is minus 30 is equal to N2 minus N1. N2 is 1.5, N1 is 1. So you will write 1.5 minus 1 divided by R. R is 10, or you can say plus 10. Now we can solve it. This is 1.5 YB, and this will become minus. Here is minus, so minus minus plus 1 by 30. This side 1.5 minus 1, it will be 0.5 divided by 10. Okay, so further we can solve it. 1.5 divided by V is equal to 0. First we can solve it. It will be 5 by 100. We can cancel this out. 5 to the 10 and 0. So it will become 1 by 20 minus 1 by 30. Okay, so now we can solve it. We can take the LCM here 60. So in between this, we can take the between the 20 and 30, we can take the LCM 60. So here will be 3, here will be 2. So it will become 1 by 60. So it will become 1.5 divided by V is equal to 1 by 60. So when you will multiply 1.5 with 60, so the image distance you will get 90, means plus 90 centimeter. So you are getting the image distance plus 90 centimeter. So plus 90 centimeter means image is forming in this direction from the pole. So image is forming at a distance of 90 centimeter, means somewhere here, at a distance of 90 centimeter. This will be the image position. Talking about the nature of the image, so in this case, how can the image form? So this is the object here. So from this object, suppose there is a ray of light like this. This is the incident ray from this object. Okay, real image is one when the rays are actually meeting, and virtual image is one when rays are just appearing to meet. So we will see whether here the image rays are actually meeting or appearing to meeting. Okay, so first ray from the object is like this, and another ray from the object is like this. So this ray will pass straight like this. Okay, wait. So another ray from the object will pass straight like this, because this is a normal incidence, pass straight like this. Okay, another ray from the object. Now for this ray, we will draw normal, and in case of the spherical surfaces, normal passes from the center of the curvature, so this will be the normal. So now light is going from air to the glass, it will bend away from the it will bend towards the normal, so this light ray will go like this, like this. So now you can see both the rays are meeting here, rays are meeting like this here. So here the image will form. These rays are meeting in actual, so the image will be the real image. This image is the real image because these rays are meeting in actual, so real image. Nature of the image is real. So there is one note point that I want to write here, and this is applicable only for the spherical surfaces. Applicable for refraction only. What is this? If uh, V and U are of opposite sign, opposite sign, then in that case the image is real. Image formed will be real. If V and U are of same sign, in that case image is virtual. So this is only applicable for the refraction. So here you can see the sign of the image distance V is plus, and sign of U, where is U, is negative, means opposite sign. So if V and U are of opposite signs, then image is real. So that is why here the real image is formed. So you, in that case, you do not have to make the ray diagram and all that. You can just easily say the image is real or image is virtual. Okay, all of you take the screenshot. Done.
Yes.
Done. Nafisa,
Yeah.
completed.
Yes, sir. Done.
Okay. So this is the all about the refraction from the spherical surfaces, and after that, uh, we will discuss lenses. We will discuss lenses. So a lens is a uh, solid transparent medium bounded by two surfaces, and in case of the lens, at least one of the surface should be spherical. Spherical means that can be in the shape of the convex or concave. So next topic is the lens. So a lens is a transparent medium bounded by two surfaces, one of which must be spherical. This is the definition. So generally, there are two types of lenses. There are other type of lenses also, but broadly we define lenses as convex lens and concave lens. So this is a convex lens. Okay, why this is a convex lens? Because this is bounded by two bulging outward surfaces, means bounded by two convex surfaces. Now this surface is the concave. Do you know cave? So this is looking like a cave now. So when light will go here, so it will look like that light is going in cave. So that is why this lens is bounded by two concave surfaces. So that is why this is known as the concave lens. Concave lens. So this convex lens, you can see this is thick in the middle. If you will draw it like this, na, it will become like this basically. So this lens is thick in the middle and thin at the edges. So for the convex lens, you can write thick in middle. And for the concave lens, you can see here, this concave lens is thick at the edges. At the ends, it is thick, and at the middle, it is thin. So you can write thick at edges. Okay. This convex lens is also known as the converging lens. This convex lens is also known as the converging lens. And this is known as the diverging lens. Diverging lens. Why this is known as the converging lens? Because when the light rays are parallel, when the parallel light rays are coming like this, for example, we can take three rays. Okay, three rays are coming parallel. So this lens converges those rays at some point like this. So that is why this lens is known as the converging lens. In this case, if the rays are coming parallel, like this, so from this lens, the rays are getting diverged. That is why this lens is known as the diverging lens. This is a convex lens. This is a concave lens. Okay. Now there are few other lenses, few other types of lenses also. Okay. We will discuss that. Further classification of the lenses in the category of convex lenses. If this type of lens you have, means this type of lens have, this surface is also convex surface, this surface is also convex surface. To identify the convex surface is basically bulging outward surface. So both the surfaces here are bulging outward. One surface is this and another surface is this. Okay. So this surface is also bulging outward. This surface is also bulging outward. So both surfaces are here are convex. So that is why this is known as the biconvex lens. Biconvex lens, or also known as equiconvex lens. Okay. Now see this type of lens. One surface is convex. This is a convex surface, and this is a plane surface. Convex surface, and this is a plane surface. So this type of lens is known as plano-convex lens. Plano-convex lens. Plano-convex lens. Plano-convex lens. Now you can see here. This surface is convex surface, means bulging outward. Now see this surface. This surface is bulging inward. Okay. So this bulging inward surface is concave surface. Concave surface. This is bulging outward. This surface is bulging outward. This surface is convex surface. This surface is concave surface bulging inward. So this type of lens is known as the concavo-convex lens. Concavo-convex lens. Mostly we will discuss this lens and this lens. Now in case of concave lens, this type of lens. Now you can see this lens is bounded by two concave surfaces. Bulging inward means concave surfaces. Okay. Concave surface. This is also a concave surface. So that is why this is known as the biconcave lens. Biconcave lens. Just give me 1 minute. Hello, Matthew, getting my voice?
Yes, sir.
Actually, my headphones battery low. So this is a biconvex lens. Why this is the biconvex lens? Because this is bounded by two concave surfaces. One concave surface, another concave surface. And another type of lens is this. Here is one plane surface and one is concave surface. So this is known as plano concave lens. Plano concave lens. Now another type of lens is this surface is concave. Bulking inward is a concave, and this surface is a convex surface. This is a convex surface, and this is a concave surface. So this type of lens is known as convexo-concave. Convexo-concave lens. So these are some types of lenses we have classified. We will discuss biconvex lens or biconcave lens. Remember the definition. What is a lens? A lens is a transparent medium bounded by two surfaces, one of which must be spherical. So here both surfaces are spherical surfaces. Concave and convex surfaces are known as the spherical surfaces. In this case, one surface is plane, another is spherical. Convex surface is a spherical surface. Okay, so take the screenshot. Done?
Yes, sir. Yes, sir.
Yes.
Okay, take this. Scroll down.
Yes, sir.
Yes.
Okay. Now we will discuss the center of the curvature and the radius of curvature of the lenses. Suppose I am polishing this. So what it will become? It will become a mirror. And what type of mirror is this? Concave mirror. Cave. Okay, concave mirror. So in case of mirror, we have seen mirror is a part of a sphere. So when you will complete the sphere like this, na? When you will complete the sphere, it will be something like that. So for the sphere, there is a center, and that center is known as the center of curvature of the mirror. Center of curvature of the mirror. So in case of mirror, there is only one spherical surface. That is why in mirror, there is only one center of curvature. In mirror, there is only one spherical surface. That is why there is only one center of curvature. But in case of lenses, there are two spherical surfaces here. In this lens, means what type of lens is this? This is a convex lens. Talking about more precisely, I can say this is biconvex lens. Biconvex. So biconvex means both surfaces are convex, and convex means both surfaces are spherical. So first surface is this. So when you will just complete the sphere of this surface, this first surface, okay, like this, okay. So you will get a center. Suppose this is C1. Now for another surface also, when you will complete the sphere like this, you will get another center of curvature. So in case of lens, there are two center of curvatures. There are two center of curvature. Same is the case with this. For this, there will be a center of curvature here. For this, there will be the center of curvature here. Understood, Matthew?
Yes, sir.
So you can write C1 and C2 are center of curvature. Okay, center of curvature. There are two center of curvature in case of lens. One more thing I told you, radius of curvature. And what was there? The radius of curvature. The radius of curvature is the radius of curvature. Means radius of the sphere is known as the radius of curvature. Na? So suppose when you will complete this sphere, for example, you are completing this sphere, try to imagine what I want to say. This is not looking like a sphere, but try to imagine this as a sphere. If you will complete this, so this is a center. So this distance will be the radius of curvature. This distance will be the radius of the curvature. And when you will complete this circle, this sphere in 3D, it will be sphere. So this distance will be radius of curvature. So what you will say now? There are two radius of curvatures in case of the lens. Okay. So first radius of curvature is this. For this is R1, and another is this, R2. Try to understand what I want to say. Okay. When you will complete the circle, you will get a center, and if there is a center, there will be the radius also. So R1 and R2 are the radius of curvatures. Radius of curvature. Okay, take the screenshot. Oh, 1 minute, 1 minute. And the line joining between C1 and C2 is known as the principal axis. One more point we will add here, principal axis. Principal axis. So what is principal axis? Line joining means this line is the principal axis. This line is the principal axis. In this case, this line is the principal axis. This line is the principal axis. Principal axis. Okay. So now you can take screenshot. Oh, sorry. Okay. Suppose if you have this type of lens. If you have this type of lens, okay. Now this is the plane surface and this is the spherical surface. This is a plane surface. This is and for this spherical surface, there will be a center. Suppose here is the center for this spherical surface, C1. Now what will be the center for the plane surface? There will be no center for the plane surface. Plane surface is a plane surface. There will be no center for it. Okay. Now radius of curvature, suppose R1 for the spherical surface. R1 is the radius of curvature for the spherical surface. Now for this plane surface, what will be the radius of curvature you will take? There will be no radius of curvature for the plane surface, but remember, for plane surface, we take the radius of curvature as infinite. Okay, so for plane surface, radius of curvature is equal to infinite. For this surface, radius of curvature is equal to infinite, and for this surface, radius of curvature is R1. Okay, fine. Now R1 is the radius of curvature for this surface. Not talking about the principal axis. How we define the principal axis for this? Here we know the line joining the center of curvatures C1 and C2 is the principal axis. In this case, we define the principal axis like this. We draw a perpendicular from the spherical surface to the mirror like this. Okay, so this line, or you can say this line, you can extend this line also like this. So this line will be the principal axis, but this should be of 90° here. Okay, a line you are drawing which is making an angle 90° with the plane surface and joining the center of the spherical surface. If you will join, okay, once again I'm telling how to do this. Okay, here will be the center of this spherical surface. Suppose this is C1. So for the principal axis, what you will do, you will just join the center of curvature, the plane surface. As such, this angle should be 90°, and you will extend that line and you will get the principal axis. If you will extend that line, you will get the principal axis. Okay, so basically this will be the principal axis. This will be the principal axis for this type of surface. Now take the screenshot again.
Done, sir.
Okay. Now there is a term in mirror, that is pole. In mirror we have, in spherical surfaces, specifically talking, in spherical surfaces we have pole. But in case of lens, we have the optical center. We have the optical center. Now what is optical center? So optical center is a point when a light ray will pass from that point, there will be no deviation. The light ray will pass undeviated. That point is known as the optical center. So optical center, a point on the principal axis, a point on the principal axis of a lens through which a ray of light passes undeviated. For example, this is a principal axis, this is a principal axis, and this is a convex lens. This is a convex lens. This is a convex lens, and this is a principal axis. And this is a point. If the light ray will come like this, if there is a light ray is coming like this and passing from this point of the lens and goes straight, so this point is known as the optical center. So it is not necessary that this optical center lie at the geometrical center of this lens. It is not necessary. Okay, it will depend upon the radius of the surfaces whether this optical center will lie at the geometrical center or not. For this also you can define the optical center. There is a point when the light ray passing from that point remain undeviated. This is a convex concave lens. Concave lens. This is principal axis. And what is this? Optical center. One more thing I want to tell you, in our syllabus, we have thin lenses. Okay, in our syllabus, we have thin lenses. And this definition is valid for thin lenses. Thin lenses. So you can write in our syllabus, thin lenses are there, very thin lenses. One more point I want to add. Earlier, I told you that in case of the spherical surfaces or spherical mirrors, all the distances are measured from the pole. All the distances we were measuring from the pole. Now, in case of the lenses, all the distances we will measure from the optical center. So all distances are measured from optical center. All the distances are measured from the optical center. Okay, take the screenshot. This ray will remain good. This will remain undeviated in case of thin lenses only. Remember, in case of thin lenses only. So in our syllabus, we will have the thin lenses, so we can say that the ray will remain undeviated. If this lens is not thin, then there will be some shift, lateral shift will be there. Okay, right. Okay. So after this, now we will define the focus. We will define the focus of the lens. So in case of the mirror, only one focus. But in case of mirror, there are two focuses, or you can say foci. So this is a concave convex lens. This is a convex lens. And focus we want to define. And first we will define the first focus. First focus. So for the convex lens, first we will see what is the first focus. This is the principal axis. This is principal axis. This line is the principal axis. So focus, first focus is defined as, suppose this is some point, and if from this point the rays are like this. if you are placing the object at the first focus, this is F1. If you are placing the object at the first focus, then rays from the first focus after passing from the lens becomes parallel to the principal axis. This is the first focus. In this way, you can define the first focus for the convex lens. Now for the concave lens, if suppose this is some point and rays of light are like this. Now the object is placed at this position. Okay. This is some point and there are some rays. Just wait. So if there are some rays, those rays are just going towards a point. Okay. This ray is going toward this point and this ray also is going towards a common point. And after passing through the lens becomes parallel. Okay. Becomes parallel. So this point is known as the first focus. F1 is known as the first focus. So F1 here is first focus. First focus. And here F1 is first focus. First focus is not that important, but you should know what is the principal focus, and this is also known as the second focus. Second focus is an important thing. This is a concave convex lens, we know. Now how we will define the first second focus or principal focus? If rays of light are parallel to the principal axis like this, if rays of light are parallel to the principal axis like this, after refraction from the lens will meet at a common point, that common point is known as the principal focus or the second focus. What I want to say that if rays are parallel to the principal axis, this is the principal axis. Rays are parallel to the principal axis after passing through the lens, meeting at a point and meeting at a common point, and that common point is known as the principal focus or the second focus. Okay, so this is known as the principal focus. Okay, after this we will define the principal focus for the concave lens. For the concave lens, so if rays of light are parallel, if rays of light are parallel to the principal axis of a concave lens, okay, after passing from the lens, after passing from the lens, getting diverged, now you can see now if a ray of light, now what I am defining, I am defining the principal focus for the convex lens. Now how we will define the principal focus for the convex lens? So this is the principal axis. Okay, now if the rays of light are parallel to the principal axis, if the rays of light are parallel to the principal axis, after refraction from the concave lens, these rays are getting diverged, and when these rays are produced back, and when these diverged rays are produced backward, these produced backward rays meeting at a common point known as the principal focus. Or you can say these diverging rays are just appearing to coming from this point. This is known as the principal focus. Understood, Matthew, Nawal, and Nafisa?
Yeah, sir.
Yes, sir.
The video was a bit laggy.
Yeah, actually, earlier also in case of mirrors also we have defined the focus something like that. Here there are some changes, but focus is basically a point where the parallel rays meet, where the rays where rays are parallel to the principal axis meet. That point is known as the focus. So in this case, little changes are there. So first focus is not that important, but you have to remember what is the second focus, and basically the principal focus you should know. Principal focus. So you can write the definition also by yourself. When the rays of light are parallel to the principal axis, after refraction from the lens, meet at a common point known as the principal focus. For this concave lens, you can define the principal focus. Light rays parallel to the principal axis, after refraction from the lens, diverged. Okay, after refraction from the lens, these rays are getting diverged, and these diverging rays when produced backward, appearing to, or you can say meeting at a common point known as the principal focus. Okay, so take the screenshot. Oh, wait. Sorry. One more thing I want to tell you. Just wait. There is one more thing. Focal length. That I have to discuss. Okay, so suppose this is the optical center O. What is O here? Optical center. We will finish the game in one shot. Okay. So optical center. Here is also optical center. Here is the optical center. Okay. Now see. We can finish focal length also. Focal length you should write here. Basically, the focal length is a distance between the optical center and the focus. Distance between optical center and focus. Okay, so now see, in this case, first define the focal length for this case. So this is the optical center and this is the focus. So this distance will be the focal length. This distance will be the focal length. F2. Okay. F2 is the focal length. Okay. In this case, what is the focal length? Distance between the optical center and the focus. So you can say distance from here to here will be the focal length. This will be F2. Accordingly, you can write F1. Here is first focus. So accordingly, with respect to the first focus, there will be the focal length F1. Distance between the optical center and focus, that this is F1. Here also you can write F1. Okay, this is F1. Now we will decide which focal length will be positive, which focal length will be negative. Very easy. This is the optical center, and now you can see here in this case, the rays are going in the direction of the incident ray is this. This is the positive direction because this is the direction of the incident ray. In this case, incident ray is in this direction. Na? Incident ray. So the direction of incident ray is in this direction, means in this direction, like this. So this direction will be considered as positive and this direction will be considered as negative. Now you can see here, this is the optical center and this is the focus. Now you want to find the focal length, and focal length is this distance, and to measure this distance you have to move from optical center to focus, because all the distances you are measuring from the optical center. So you will measure the distance from optical center to f1. So you are moving in the opposite direction of the incident ray. So this focal length will be f1, in this case will be negative. Okay. Now tell me, Matthew, this f1 will be positive or negative? Matthew, tell
It will
me.
be positive, right?
Yeah, it is positive. This is positive because to measure this distance, you will move from optical center to like this. Means you are going in the
To the right, so that's it.
direction of in the direction of the incident ray. So this is the direction of the incident ray. This is positive, okay? Now, this is very important. This is the direction of the incident ray. Incident rays is going in this direction. So you are measuring the focal length, means this distance. So you will move in this direction, means this f2 will be positive and this f2 will be negative. Okay. Focal length is also finished. Now you can take the screenshots. How many of you have seen the FIFA final?
I saw, sir.
And to which team you were supporting?
Uh, I was kind of supporting France because I didn't really want Argentina to win.
Okay.
Yeah, but
And
Mbappe played
Nafisa?
very good though.
Yeah, Mbappe. I know. Okay, take the screenshot.
Yeah, done, sir. Who are you supporting, sir?
Obviously, Argentina, due to Messi.
Oh, all right, all right.
Taken?
Yes.
Uh, Naval taken?
Yes, sir.
And Naval, which team you were supporting?
Argentina.
Okay, so take this screenshot. Taken?
Yes.
Matthew, tell me one thing. Between Ronaldo and Messi, what do you think? Which one is better player?
I don't know. I kind of prefer Ronaldo more, but then at the same time, I feel both of them are equally as good, because it's way more harder to win with Portugal than to win with Argentina. I personally think. And Ronaldo pulled that out in 2016. Yeah.
Okay. So in this way, you have to decide the sign. the direction of the incident ray you will consider positive, and the direction opposite to incident ray you will consider negative. So tell me, Matthew, during the class, is there any time, means is there my voice breaking or video breaking,
Yeah,
or is
so
it all
your
right
voice is kind of breaking now. Your
now?
voice is breaking now. Yeah, it was breaking when you was asking me that.
Yeah, okay, understood. Okay, so now we will meet in the next class. Okay, so remember these points.